The most dangerous moment in a large-scale electrical disruption is not the instant the lights go out, but the silent interval that follows when communication channels begin failing one by one, severing the invisible threads that coordinate response, distribute information, and maintain social stability. In an EMP or widespread grid failure scenario, the collapse of electronic infrastructure does not merely interrupt convenience. It fractures the flow of situational awareness, leaving individuals and institutions operating with incomplete data at precisely the moment when uncertainty is highest. The danger emerges from this informational vacuum because without reliable communication, even minor disruptions can cascade into systemic failures as coordination breaks down, response times lengthen, and misinformation fills the void left by verified signals. What makes this phase uniquely hazardous is that its effects propagate faster than physical damage, spreading through networks of dependence that modern societies rarely perceive until they stop functioning. From an analytical standpoint, communication systems are layered structures built on power, availability, signal propagation, and network synchronization, each component relying on precise timing and electromagnetic stability. An electromagnetic pulse or large-scale outage disrupts these foundations simultaneously, damaging sensitive electronics, overloading protective circuits, and eliminating the energy required for signal transmission. Even devices that survive the initial event may become functionally useless if supporting infrastructure such as repeaters, cellular towers, or internet backbone nodes are offline. The analytical challenge is therefore not simply device survivability, but network survivability, because communication effectiveness depends on both endpoints and the pathways between them. Understanding this distinction is critical as it shifts preparedness away from focusing solely on protecting individual gadgets toward ensuring alternative methods of signal exchange that do not rely on centralized systems. A widespread misunderstanding arises from the belief that possessing communication devices automatically guarantees connectivity, leading many to stockpile equipment without considering compatibility, power sustainability, or the limitations of range and interference. This assumption is reinforced by everyday experience with seamless connectivity, where networks self-correct and signals route automatically, masking the complexity beneath. Another misconception is the expectation that emergency services will remain fully operational regardless of infrastructure damage, overlooking the reality that responders depend on the same power grids and communication backbones as the public. These beliefs create a false sense of preparedness, where the presence of hardware substitutes for a functional communication plan, leaving individuals vulnerable when systems behave differently under stress than they do under normal conditions. The hidden science that explains communication resilience lies in electromagnetic compatibility, signal attenuation, and redundancy principles, which together determine whether information can traverse a disrupted environment. Electromagnetic pulses induce currents in conductive pathways, damaging semiconductor junctions and overwhelming surge protection, while the absence of grid power eliminates the amplification and routing functions that extend signal reach. However, lower-tech communication methods operating at reduced complexity often demonstrate higher survivability because they rely on fewer vulnerable components and can function with minimal energy. Signal propagation at different frequencies also interacts uniquely with terrain and atmospheric conditions, meaning that communication range and clarity depend on both equipment design and environmental context. This interplay reveals that resilience is less about technological sophistication and more about understanding how signals behave when stripped of supporting infrastructure. Evidence from historical blackouts, solar storm impacts, and controlled electromagnetic testing shows consistent patterns in system degradation, where highly integrated networks fail rapidly while decentralized, low-power communication methods persist. After major outages, communities that maintained independent radio communication capabilities were able to coordinate resource distribution and emergency response more effectively than those relying solely on disrupted digital networks. Engineering studies further demonstrate that devices shielded from induced currents or disconnected from long conductive lines exhibit significantly higher survival rates, reinforcing the importance of both physical protection and operational planning. These findings illustrate that communication continuity is achievable, not through a single protective measure, but through a combination of hardware resilience and procedural readiness grounded in known physical principles. The survival implications are profound, because communication is the mechanism through which information becomes action, enabling coordination of medical care, resource allocation, and security measures. Without reliable channels, Decision-making becomes localized and reactive, increasing the likelihood of duplicated effort, overlooked hazards, and delayed response to emerging threats. Conversely, even limited communication capability can stabilize a situation by restoring the flow of verified information, reducing uncertainty, and allowing collaborative problem-solving to resume. In this way, maintaining communication is not merely a convenience, but a force multiplier that amplifies the effectiveness of every other survival strategy. As the disruption persists, escalation occurs through the gradual depletion of backup power systems, battery reserves, and fuel for generators, shrinking the operational window for surviving communication equipment. Environmental factors such as weather, terrain, and urban interference further complicate signal reliability, while the psychological strain of isolation increases the urgency of restoring contact. At this stage, the challenge shifts from initial survival of devices to sustained operation, where energy management, signal discipline, and procedural coordination determine whether communication remains viable over time. The system evolves from a technical problem into a logistical one, demanding both engineering awareness and behavioral adaptation. This progression leads directly into a deeper examination of how decentralized communication strategies, energy-efficient signaling, and environmental awareness can be integrated into a cohesive approach that preserves information flow despite infrastructure collapse, revealing that the most reliable communication method is defined not by its speed or convenience, but by its ability to function independently of the systems most likely to fail first. Once the initial shock of an EMP or widespread grid failure has passed, the danger shifts from immediate device loss to the progressive fragmentation of networks, where partial functionality creates the illusion of connectivity while critical pathways remain compromised. In such scenarios, individuals may possess radios, satellite phones, or other communication devices, yet without accessible repeaters, functional power sources, or compatible frequencies, these tools are effectively isolated. The analytical insight is that survivable communications depend not on the mere presence of equipment, but on the integrity of the entire transmission chain, from signal generation to reception, including the environmental and infrastructural context. Even small misalignments, such as mismatched frequency bands or inadequate antenna orientation, can render a sophisticated device useless in real-world conditions, demonstrating that technical survival requires rigorous planning rather than ad hoc deployment. A persistent misunderstanding is the assumption that emergency power alone guarantees operational continuity. Batteries, solar panels, or generators provide energy, but without a comprehensive understanding of load demands, surge protection, and energy conversion efficiency, the runtime of critical devices is often overestimated. Overdrawing power can damage circuits, while intermittent operation reduces signal reliability, creating vulnerabilities precisely when consistency is most essential. Furthermore, many survivors neglect the importance of physical shielding, ignoring that conductive paths can channel induced currents into delicate components during an EMP event, compromising functionality even when energy is available. These overlooked principles illustrate that resilience is determined as much by engineering discipline and protective practices as by the choice of devices. The hidden science underlying these vulnerabilities involves electromagnetic pulse physics, surge propagation, and energy conversion efficiency, all of which define the survivability and effectiveness of communication equipment in extreme conditions. EMPs induce high-voltage transients in conductive materials, producing currents that exceed the tolerance of unprotected semiconductors and integrated circuits. Signal degradation can also occur through partial coupling, reflection, and interference, particularly in urban environments with complex metallic infrastructure. Understanding these interactions allows the design of low-tech but resilient communication strategies, such as shortwave radios with simple circuitry, Faraday shielding, or line-of-sight relay networks that bypass vulnerable centralized nodes. This science emphasizes that the most durable communications often rely on predictable physical principles rather than complexity or miniaturization. Empirical evidence from controlled EMP testing and real-world blackout events confirms these principles, showing that highly integrated, network-dependent devices fail rapidly, while robust, low-complexity alternatives maintain basic functionality. Field studies in post-disaster urban areas consistently reveal that communities leveraging shortwave, VHF, or UHF radios, particularly when protected in grounded or shielded enclosures, maintain operational coordination far longer than those reliant on grid-connected digital systems. Practical engineering assessments demonstrate that even improvised Faraday cages, constructed with grounded metal enclosures or layered conductive shielding, can significantly reduce induced currents, allowing essential devices to function post-event. This data underscores that survivable communications are less about high-end technology and more about system awareness, environmental adaptation, and physical protection. The survival implications of maintaining communication capability are extensive. Reliable messaging enables coordination of limited resources, timely dissemination of hazard information, and orchestration of medical or security responses. In contrast, groups lacking operational communication tools experience slower response times, increased risk of resource conflicts, and elevated exposure to environmental hazards. Even minimal connectivity can have a multiplier effect, allowing a single informed individual to relay critical instructions across multiple locations, stabilizing the broader survival network. The strategic importance of communications extends beyond information transfer. It preserves structure and decision-making capacity within populations otherwise vulnerable to chaos induced by uncertainty. As conditions persist, escalation emerges from compounding technical and environmental factors. Power sources deplete, devices succumb to fatigue, interference from debris or atmospheric conditions reduces range, and human cognitive load increases as vigilance must be maintained continuously. This phase highlights that communication resilience is not static. It is an ongoing operational process requiring monitoring, adaptation, and disciplined resource management. Energy must be rationed strategically, signals prioritized to convey critical information, and redundancy built into both hardware and procedures. A failure to recognize these compounding dynamics transforms survivable disruptions into cascading failures that undermine broader survival efforts. Transitioning from theory to practical strategy requires integrating the physics of EMP impact, energy management principles, and procedural discipline into a holistic communication plan. Survivors must consider not only the devices themselves, but their placement, shielding, power provisioning, and the environmental factors that influence signal propagation. By combining redundancy, simplicity, and predictable physical principles, it becomes possible to maintain a functional communication network even when the centralized infrastructure has collapsed. This realization underscores a fundamental truth. The most effective survival communication system is not defined by sophistication, but by reliability, repeatability, and independence from vulnerable systems. At this stage, the danger intensifies as individuals and groups face the dual threat of equipment degradation and environmental interference, where even modest connectivity can vanish if power reserves dwindle or antennas are misaligned. EMPs and grid blackouts do not affect all components equally. Some circuits may survive initial surges, while others fail instantly, producing unpredictable functionality that complicates coordination. Survivors who fail to anticipate this partial degradation often overestimate their capacity, assuming that a single working device ensures continued communication. In reality, operational reliability depends on layered strategies that account for both hardware survivability and environmental constraints. Because a single point of failure, even in a seemingly minor component, can sever the link between dispersed units, erasing situational awareness and delaying critical responses. Analytically, communication resilience is a function of redundancy, energy efficiency, and signal adaptability. Redundancy ensures that if one device or frequency fails, alternative channels can maintain information flow. Energy efficiency extends operational duration, requiring careful assessment of load, voltage regulation, and the relative consumption of each device. Signal adaptability addresses environmental variables such as terrain, atmospheric conditions, and physical obstacles that impede propagation. Survivors must evaluate these factors in tandem, because effectiveness is determined not by any single dimension, but by the interaction of all three, creating a multivariable optimization problem where even small miscalculations can reduce network functionality dramatically. Recognizing the interdependence of these factors transforms preparation from simple equipment stockpiling into a disciplined engineering exercise. A common misunderstanding is that short-term solutions will suffice for extended disruptions. Many assume that charging devices before the event or having spare batteries is enough to sustain operations, overlooking both the degradation of stored energy over time and the cumulative effect of repeated surges or partial failures. Another misconception is that complex devices provide inherent resilience, ignoring the vulnerability of highly integrated circuitry to transient voltages and EMP-induced currents. This error often leads to over-reliance on digital tools while neglecting simple, robust alternatives, such as low-power analog radios, mechanical signaling, or pre-established relay networks. These misunderstandings highlight the importance of assessing survivability through systemic analysis rather than intuition or anecdotal experience. The underlying science that informs this assessment is grounded in electromagnetic theory, circuit tolerance, and signal propagation dynamics. EMPs generate high-intensity, short-duration electrical fields that induce damaging currents along conductive paths. Circuit design, component selection, and shielding effectiveness determine the degree to which a device survives such events. Simultaneously, signal propagation depends on frequency, antenna design, and environmental reflection or absorption, illustrating why range and clarity can collapse even when power remains. Understanding these physical principles allows planners to predict vulnerabilities, select appropriate technologies, and implement protective measures that significantly enhance the probability of maintaining operational communication post-event. Empirical evidence demonstrates that systems designed with simplicity, physical protection, and operational discipline consistently outperform more sophisticated but unshielded or unplanned configurations. Field reports from EMP simulations and prolonged grid outages reveal that low-tech, manually operated radio networks sustain communication across wider areas and longer durations than complex digital networks, reliant on continuous energy or centralized infrastructure. Controlled laboratory testing confirms that modest Faraday enclosures, grounded metallic barriers, and careful separation from conductive lines markedly improve survival rates of electronics exposed to EMP pulses. This combination of real-world observation and experimental data underscores a critical survival insight. Predictability, protection, and repeatable operational procedure matter more than the apparent capabilities of individual devices. The survival implications extend beyond the preservation of individual communication devices, because maintaining information flow is directly linked to decision-making efficiency, resource distribution, and emergency response coordination. Groups with resilient networks can issue warnings, allocate limited supplies, coordinate medical care, and maintain security protocols, whereas isolated units face compounded risk from delayed situational awareness. Even minimal network continuity can amplify organizational capacity, enabling a single informed node to disseminate critical updates across multiple recipients and stabilizing otherwise vulnerable populations. This reinforces the idea that communication is not a peripheral concern, but a central pillar of sustained survival strategy. As time progresses, escalation arises from the interplay between energy constraints, human fatigue, and environmental interference, creating a dynamic